All right, our discussion of momentum centers on two big equations, maybe three. But momentum, by definition, is the product of mass and velocity. And that tells you what the units of momentum are. Well, mass is measured in kilograms, and velocity in meters per second. So the units of momentum are just that, kilogram meters per second. Simple as that. There's no fancy way to, well, there is a kind of a fancier way to do that, but that's the most common way. Okay? Yeah, one of the big deals that we talked about is there's this thing called impulse that by definition is change in momentum, right? J is delta P. Well, how do you change an object's momentum? Two ways. Since that's true, well, change its velocity. How do you change something's velocity? Apply a force to it over some amount of time. Okay? So very common to see situations where they will tell you three of those things and ask for the fourth. Use that. What are you really using? You're really using that. It's the same thing. If we just write that as M, A is delta V over T, or delta T, right? Then you multiply both sides by delta T, and you get this. Okay? But very, very common to get three of these and be asked to find the fourth. Okay? It's also very common to be asked to look at this situation graphically, right? And so they can show you something like this. If we have a graph of force versus time, and that graph, say, well, oh, I don't know, looks like this, well, in this case, what I would do is say, let's find the average force. Here's what's called the average force. Should probably be a little lower. Yep. Average force. We could say from this graph, if, well, here's some delta T. We could say that, well, the impulse is F delta T, and that's actually the area of that box. So impulse for this graph is area. Okay? And you don't actually even have to find the average, but it's probably the more common situation that they would just give you a constant force like that. Okay? So you have a force, you have a time, multiply them together, F delta T, that's the impulse. That, yes, also happens to be the area of this box. Okay? And that means that, notice, since this is in newtons and that's in seconds, you can measure impulse in newton seconds. Not newtons per second, newton seconds. Okay? The other big thing in momentum is two-object interactions. And anytime that two objects interact, conservation, momentum is conserved, which means you have the same amount in the beginning, the same total momentum in the beginning, and the same total momentum afterwards. We ended up writing that like this. Long equation, but you should be comfortable with it. All right? And two big situations that you'll see. Right? Let's have something like this. You have like a big mass and a smaller mass, M1 and M2. And they're held together by a spring, and then that spring is released, and M1 goes this way. So I would say that these two things, V1I equals V2I, is 0. You let these things go. M1 goes that way at V1F, and M2 goes this way faster at V2F. Why faster? Well, here, the initial momentum, the sum of all the initial momentums is 0 because of this. So that means that the sum of the final momentums has to be 0. So that means that momentum 1 final plus momentum 2 final has to be 0. And that means that, well, they have to go in opposite directions. Momentum is a vector, so the directions that things move in are super duper important. All right, this would have a negative momentum if we say left is negative. This would have a positive momentum if we say right is positive. And we can add those up and get 0. Okay, so here we would literally take this whole side of the equation and make it 0. And say that m1 v1f plus m2 v2f is 0. Or that m1 v1f is negative m2 v2f. And you can find whatever you wanted to find. Okay? The other big case for this is if we have two objects that are moving in the beginning, and they come and stick together. Come on. So you got a case like this. M1, V1 initial. Let's just take this, M2. Let's say it's not moving, right? And then these things, M1 comes and whacks into M2, and they stick together. We call that an inelastic collision. Well, these are now going to move. Wait, I said V1F. That's really V1 initial, excuse me. And they would have some, well, common final velocity. Okay, so what we'd say here is, well, M1, V1 initial, plus, well, I'll write the whole thing out, M2, V2 initial, M1, V1 final, M2, V2 final. Well, that whole thing would go away because this thing is not moving. All right? And then, because of this, this is a special situation. They have the same final velocity. So I would write this like this. M1, V1 initial equals M1 plus M2 VF. So pretty common to be asked to find that final velocity. VF M1 V1 initial divided by the sum of the two masses. Okay? But the big concept, the big old idea is this. That momentum is what's called a conserved quantity. All right? There's always the same amount of it before and after any interaction between two objects. That assumes, of course, that that there's no friction and all that sort of stuff. Okay? All right.